Well, today I'd like to start talking about op-amp design. We'll spend a lot of time in the course talking about op-amp design. First, a review from last time. We asked the question how an amplifier differs from an operational amplifier. And the big distinction we made is the size of the gain and the fact that one is intended to be used in open loop applications and the other in closed loop applications. We also asked the question, what's an operational amplifier? And I did that. I spent a whole period talking about that almost, because I think it's important to clear up a misconception that exists in the field. The emphasis is that it's not a voltage amplifier with a high gain, with a high input impedance and a low output impedance. And it's not a device that has differential inputs and single-input outputs. It can be much more general than that. We saw that there were a multitude of different amplifier structures that could be called an op-amp. They could be single-ended or differential at the input. They could be single-ended or differential at the output. And the port terminals could be either current or voltage on either port. Really makes no difference. We saw that, we also observed that there were a lot of other characteristics that we would like to have in an operational amplifier. At least that's the conventional wisdom. Low output impedance and high input impedance if it's a voltage amplifier. Large output swing irrespective of the type. Large input range usually irrespective of the type. We've got to be careful here because it may be the case that you are looking at applications where you're not going to put a very large input in. If you don't have a requirement there'll be a large input, then having a large input range is not a big deal. A lot of times you like to have a large output swing. That's true for catalog parts. But in many applications, your output swing might only be 100 millivolts. So who cares if it has the ability to swing a long ways if you're not going to swing it a long ways? Many times we want good high frequency performance, but we've got to be careful because good high frequency performance oftentimes means we get a lot more noise than we need. So sometimes not good high frequency performance is actually better. A lot of times we like to have fast settling. Sometimes we don't want to have that. Usually we want adequate phase margin, typically a good common mode rejection ratio, typically a good power supply rejection ratio because we don't want to have stiff requirements on the characteristics of our power supply. We almost always would like to have low power dissipation, although on grid connected equipment, low power dissipation is not so important. We would like reasonable linearity, irrespective of which of the types we have. And the reason we would like reasonable linearity is when we apply feedback, the feedback dramatically improves the linearity, but it doesn't completely eliminate all the nonlinearity. So if we're reasonably linear to start with, we're better off. So we saw that conventional wisdom on what an operational amplifier is does not guide us in regard to what we really need to do when we're designing operational amplifiers. Even though I picked this example of the operational amplifier to show where I think that conventional wisdom misleads us, we could take several other topics. I won't do it in here right now, of things that I think that you've been indoctrinated to think in a certain way that probably is not the right way to think. So I need to point out that just because it's published doesn't mean it's correct. Just because famous people convey the information as fact doesn't mean they're right. So keep an open mind about everything that's done and always ask the question whether the approach others are following is leading you in the right direction. So much for the fundamental amplifier design issues. Let's now talk about single stage low gain op amps. And we'll eventually talk about single stage high gain op amps and two stage op amps and other ways to increase the gain of the amplifier because we saw what was important is a high gain. So here's our three different types: single-ended input, single-ended output, differential input, single-ended output, or differential input, differential output. And in what follows, I don't want to necessarily try to distinguish between these four types, the same, or these three types. The same issues apply for all three types. So let's look first at the single-ended input structures. If we have a transfer characteristic of an amplifier that goes from some high level to some low level, then in between we have a gain. And if that slope is fairly steep, we have a high gain. If I put a tangent line in at a Q point, I can say that output is certainly a function of Vn. That's a nonlinear function. But in the neighborhood of the Q point, it's equal to minus A times Vn minus Vnq plus Vyq, where Vyq is this vertical axis intercept. So this is the average running moment. Excuse me just a second. When operating near the Q point, the linear and nonlinear model of the amplifier are nearly the same. If you're in this region right here, you can't see much difference between the linear model and the nonlinear model. If the gain of the amplifier is large, so that's nearly a vertical line, Vxq is the character of the amplifier, where that transition occurs. So now let me take the structure, it has this type of transfer characteristic, and apply feedback. And this is the standard non-inverting amplifier architecture. And I can sum currents at this node, and I can put in the model for the amplifier. So if I sum currents at this node right here, I get this equation. The top equation is the model of the amplifier. And notice in those two equations, I have one extra unknown, and that's V1. So I can eliminate V1, and I get the relationship between the output and the input to this feedback amplifier. So V out is equal to minus A times, oh, that's kind of a nasty expression. If I define the small signal input to be what I add to the Q point input to form the overall input, then I can plug this back into this equation here, and I have the relationship between the output, the small signal input, and the quiescent values of the X and the Y coordinates. This is more work than what we did in 230, isn't it? But I'm not assuming that A is infinite right now. Now, if A is large, then this becomes large compared to 1, so I can neglect the 1. The A's will cancel, and the R1 plus R2s will cancel. So I'm left with minus R2 over R1 here, times V in small signal plus V in Q. If the A's are large here, this becomes then the A's cancel. And this is 1 plus R2 over R1 times Vxq. And if A's are large, this disappears. So for a large slope on this single-ended input, single output structure, the output is approximately equal to minus R2 over R1, V in small signal, plus Vxq, plus R2 over R1 times Vxq minus Vnq. Okay. Now, as long as A is large, so I get this equation, and if V in Q is close to Vxq, which is where the transition occurs in the amplifier, then this term disappears. And we see the output is equal to the Vxq, parameter of the amplifier, where the transition occurs, plus the gain times the small signal input. That's what we want an amplifier to do, isn't it? We want an amplifier to amplify the input, and it has to be at some quiescent point. So the out's approximately to minus R2 over R1, V in small signal, plus quiescent output. And the quiescent output's at the same level, approximately as the quiescent input. So the next question is, if we're going to build op amps, we're going to build these relatively low gain op amps that have this type of transfer characteristics. What type of circuits have the transfer characteristics that kind of look like this? Have we seen circuits that have a transfer characteristic that looks like this? What? An inverter. We saw inverters in 330. So let's look at this circuit here. We have a special name for this circuit on the left. What's the circuit on the left called? What's the circuit on the left called? Common what? Common source amplifier. Right? And so this is a basic structure. We thought of it as an open loop amplifier before, but now I'm looking at it as an operational amplifier. Single transistor operational amplifier. And the gain with feedback is about R2 over R1 in the feedback configuration we looked at. Now on the right, there's a practical implementation where we implement a current source with a transistor M2. And we talked about doing that in 330 using a transistor to implement a current source. And I've also added a capacitive load to include the frequency-dependent effects in the amplifier gain. When you lay the circuit out, there's parasitic capacitances on the nodes. We didn't talk about that much in 330, but there's a diffusion that forms the drain of M1, or here there's a diffusion that forms the drain of M1 and the drain of M2. Those diffusions are p-n junction. We talked about a p-n junction being a varactor diode. So there's a certain capacitance associated with that. So CL models that capacitance. It also models any additional capacitance that might be associated with interconnecting this amplifier to something else. Is this a new concept? Thinking of this common source amplifier as an op amp. This is not a new idea. I made a reference to this earlier. This is an application note that came out in 1973 from National Semiconductor. And here they were proposing using the CMOS inverter, the logical inverter, as an operational amplifier. So we just analyzed the circuit that they've been looking at. Let me briefly review sinusoidal steady state analysis, because I'm not exactly sure how your background is on phasors relative to S-domain analysis. So the standard approach to circuit analysis, if we stay in the time domain, is to have an input to our circuit, Xn of t. We have a time domain circuit. And if we analyze that time domain circuit, we end up with a set of differential equations. If there's no energy storage elements, there'll be a set of linear equations. If there are energy storage elements, there'll be a set of differential equations. Then we solve the differential equations to get the output. Of course, we don't like to do it this way because it takes too much time to write the differential equations and solve the differential equations. So the approach that I think is followed in 201, we do a phasor transform if the input happens to be a sinusoidal signal. And then we have a phasor input. Then we take the time domain circuit and we do a phasor domain transform of the time domain circuit. So we replace inductors with impedances of j omega L, capacitors with impedances 1 over j omega C. And then we analyze the phasor domain circuit. And this gives us a set of linear equations in J omega. Then we solve those linear equations because it's a linear circuit. We're making the assumption it's linear. And then if we want to get back to the time domain output, we do the inverse phasor transform, and we get x out of t. Is this how you did it in 201? Yeah. Yes. Okay. Alternatively, we can do the Laplace transform or the S transform of the input. We can do the S domain circuit instead of the phasor domain circuit. We can analyze the circuit in the S domain. Gives us a set of linear equations in S. We can solve these linear equations in the S domain. And then we can do the inverse S transform or the inverse Laplace transform and get x out of t. Did you guys do this in 201 also? 230. Pardon?
That was more. 230.
230 more. Okay. So I'm going to stay in the S domain instead of the phasor domain. They're really exactly the same analysis. And from 330, we talked about, we're doing a small signal analysis, how we map all of our elements to a linear small signal element, our resistors, our capacitors, our dependent sources, and our active devices, and so forth. If we look at input, we're interested in the input and the output, then we have a linearized circuit. We then start with the Laplace transform of the circuit, or the S transform. No, I'm sorry, we take the Laplace transform of the input, and that gives DMS, put it in the S domain circuit, and then put that into the transfer function TVS to get the output. So the transfer function is the relationship between the S domain output and the S domain input. And you'll recall that if we want to find the steady state response, then if we have a transfer function, the steady state output is equal to the magnitude of the input. I'm assuming the input is Vm sine omega t, times the magnitude of the transfer function at the frequency of excitation, times the sine omega t plus theta plus the angle of the transfer function. So that should have been material from 230 and 201 as well. Now let's go back to our operational amplifier that we're looking at. And I can look at the small signal models of the amplifier. If I put an ideal current source in, I put in the model of the MOS transistor. GM-VGS is the dependent current source. G-out is the output conductance. I'm loaded with capacitor scale. Or if I put in the current source, you'll recall the small signal equivalent of that current source was just a conductor of value G out. So the model of this amplifier circuit has G out 1 plus G out 2 here. I can calculate the transfer function pretty easily at this point. And by definition, the transfer function is the gain. It's a relationship between the Laplace transform of the output, Laplace transform of the input, and it's equal to minus GM over SCL plus G out. Or if we have the non-ideal current source, the gain is minus GM1 of the lower transistor over SCL plus GL1 plus GL2. So now we've got the S domain gain of the operational amplifier. The DC voltage gain is a ratio of the overall transconductance gain to the output conductance. Can we see that? The DC gain of this open loop gain, it's the slope of that transfer characteristic at the Q point, evaluated at 0, and it's minus GM over G out. Or for this structure, it's minus GM over GL1 plus G out 2. Observe that in either case, the small signal equivalent circuit is a 2-port of this form. There's a transconductance device that multiplies the input voltage, and there's a conductance G That conductance G is either G out 1 or it's G out 1 plus G out 2, depending on which circuit we look at. So we can claim that all properties of this linearized circuit are determined by the two parameters, Gm and G. Okay. Alternately, we can do a Thevenin to Norton transformation or a Norton to Thevenin transformation and put a voltage-dependent voltage sources here instead of a current-dependent, a voltage-dependent current source. And in that case, this voltage-dependent voltage source has value minus Gm times 1 over G right here. So these are two equivalent forms of this amplifier with an output in either Norton form or Thevenin form. So in this case, all properties of the circuit are determined by AV and G. Same G, but now AV. So let's get a couple of properties of this op amp, this single-inlet op amp. We see the DC gain is now minus Gm over G. The bandwidth, we see the bandwidth. The bandwidth is the pole location, a first order system, and we're negative the pole location. So the pole is G over CL. So the bandwidth is the negative of the pole, so it's G over CL. And the gain bandwidth product, take the product of the gain and the bandwidth, the G's cancel, and it's Gm over CL. These are two of the most important parameters of most op amps, the gain and the gain bandwidth product. Now, this applies to any single output amplifier. The examples I look at happen to have either 1 or 2 transistors in them. There could be 50 transistors in them. But there exists a Norton equivalent or Thevenin equivalent circuit characterized by two parameters, Gm and G. And the gain bandwidth product and the bandwidth and the gain are always given by these expressions. For notational convenience, this conductor G here is oftentimes referred to as the output conductance of that two-port model. So oftentimes we use G out to model that. Okay, so in this context then, capital G and G out are the same. G out is not referring to the output conductance of a single transistor. G out is referring to the output conductance of this whole op amp. If you want to design a circuit and you look at the parameters Gm and G out, which determine the gain and the bandwidth and the gain bandwidth product, they give us almost no insight into how to design this circuit. So let's go back now and talk about designing this op amp. How do we design an amplifier with a given architecture in general, or this architecture in particular? So I will go through details with this architecture, but what I do can apply to any architecture, whether it's single-ended or differential at the input, single-ended or differential at the output, and so forth. So we asked the first question, what's the design space that we're involved with here? What's our design space? I'm going to assume, what?
The transistor size.
So the design space, transistor size, so let me write down first of all what we have to do to completely uniquely characterize the circuit. If we know W and L and VSS and VDD and V and Q, and CL, VNQ, VSS, and IDQ. We completely know everything about that circuit, right? However, usually VDD and VSS are constraints. They're usually given. The load capacity is usually given. So that reduces it to a design space of 4 values. Right? However, in our device models, W and L always appear as a ratio. So that reduces it to three design variables. But there's a relationship. What?
So the ID related to W over L and V and Q.
Yeah. So ID is related to V and Q and W and L. So there's a constraint. So these are the design variables. But there's one constraint. And that is IDQ is equal to some function of W over L, V and Q. So we can think of this as a two-dimensional design space. So the design space is comprised of, and I can pick any two of these three as the independent variables. W over L and IDQ. Okay? Makes sense what we're doing? Trying to understand our design space. So the design of this circuit, or synthesis with this architecture, involves exploring this two-dimensional design space. For every value of W and L and IDQ, I'll get a different op-amp. Some of the op-amps may be better than others.
Could you repeat what you mean by design space?
Yeah. If you have a system that has a certain number of things that you can choose, then the question is how many of those can you choose independently? And I define that to be the design space. So in this case, I'm assuming the supply voltages are fixed, the load is fixed, and the circuit structure fixes the relationship between IDQ and V and Q and W and L. So that means there's only 2 degrees of freedom left. So our design space is really reduced to a two-dimensional design space, or 2 degrees of freedom.
So it's essentially choosing independent variables.
What?
It's like choosing independent variables.
That's right, 2 independent variables. And different values for those 2 variables will give me different op-amps. Different op-amps will have different characteristics. So a strategy is, first of all, to determine the design space. There are actually 4 design variables, but the design space gets reduced. Identify the constraints. And the constraints are W over L appears only as a ratio, and there's a relationship between the drain current and W and L and the quiescent input. Then we have to determine an appropriate parameter domain to design this circuit in. Well, one parameter domain is what we might call the natural parameter domain. I look at these as natural parameters. It's pretty easy to get to this point, isn't it? Of course, the number of parameters that we have in our design space should be equal to the number of degrees of freedom we have. The parameter domains for characterizing the design space are not unique. So WRL and IDQ form a two-parameter design space. But there are other two-parameter design spaces we'll talk about in a bit that could also be used to characterize this design. And once we know what our design space is, then we want to explore that design space. So if you have a two-dimensional design space, it could be W over L and IDQ. At any point in this design space is a new amplifier. Of course, we may be constrained. W over L may not be able to get over so small. IDQ may not be able to get over so small, or may not be able to get over so big. W over L, I guess, can probably be arbitrarily big. So our realistic design space that we might want to explore might look something like this. Let's talk a little bit about the parameter domains then for characterizing amplifier performance. The parameter domain should give us insight into the design. If I use W over L and IDQ as a design space, the parameters should be independent. We wouldn't want parameters in our design space to be dependent upon each other. It needs to be a minimum size. That is, it has to represent degrees of freedom in our design. And hopefully it will have reasonably simple design expressions. And we'll see what we mean by that in a minute. Most authors don't talk much about either the parameter domain or how you use these parameters in the design. So this is something I think is important that's a lot of times overlooked. So let's go back to that op amp again now. And this amplifier is characterized by GM and G out. So I could think of this as the small signal parameter domain. And there's two parameters in the small signal parameter domain. So this could be our design space. There's 2 degrees of freedom here. But there's very little information in this parameter domain about how the circuit performs. The natural parameter domain we just talked about is W over L and IDQ. Also has 2 degrees of freedom. And I call this the natural parameter domain. In the natural parameter domain, I'd like to then to get the parameters of interest. I'm going to assume that in this case I'm interested in the gain bandwidth product and AV. I could be interested in other things, but let me focus on GB and the gain. So the GB is GM over CL, and the voltage gain is minus GM over G out. We've got a problem. Because these parameters in the two-dimensional space don't appear in the expressions for GB and AV. However, we can write GM in different ways. 2 IDQ over V excess bias. Mu CX W over L times V excess bias. Or the square root of 2 mu CX over L times the square root of IDQ. If I express GM this way, it involves only the 2 parameters that are in the parameter domain and process parameters that are characters of the process. If I express it this way, it has a different parameter that's not in our parameter domain. If I express it this way, it has a different parameter that's not in our parameter domain. And G out, which appears in this expression, is lambda IDQ. Well, in this case, lambda is a process parameter, and IDQ is one of the parameters in our parameter domain. Now, I don't quite have GB yet, but from GM and G out, I can get the voltage gain by taking that ratio. I can take the ratio to get the voltage gain. And I can take the product of, I already have the gain bandwidth product here. So I can write down the gain bandwidth product also in terms of the natural parameter domain. And if I do that, I find the gain can be expressed like this, and the gain bandwidth product can be expressed like this. So now I'm starting to get into some insight into the design, because my parameters of interest are now expressed only in terms of my design variables, W over L and IDQ, and parameters which I can't control, which are characteristics of the process, mu, Cox, lambda, and CL. Okay. Unfortunately, if I want to explore this design space, the expressions are quite complicated. I've got a square root of W over L in the numerator and a square root of IDQ in the denominator here, and for GD I've got a square root of W over L in the numerator and a square root of IDQ in this case in the numerator. And both expressions are dependent upon both variables in my parameter domain. Is that clear? So if I change W over L, I change both the gain and the gain bandwidth product. If I change IDQ, I change both the gain and the gain bandwidth product. Is that convenient? No, it's not. If you're trying to optimize the gain or optimize the gain bandwidth product, you change one and the other changes too. So it does give us a little bit of insight into the design, but the expressions are complicated and designing in this parameter domain is somewhat complicated as well. Let me make an observation. If I reorder the parameters, this parameter here, this is the gain, this parameter here is process dependent, but not design dependent. And you can show that this parameter here is architecture dependent and not process dependent. So if I want to compare different amplifier architectures, I can look as a figure of merit, be the ratio of AV0 to this. And that will be not dependent upon the architecture. So all architecture information would be in whatever this term here is in the right. Does that make sense? So if I have two circuits, this part will be the same for the two circuits. I can always normalize so that's the case. And if I want a larger, compared to architectures, if one has a bigger value than the other one here, I know that one has a higher gain. Is that useful? Well, oftentimes we have to compare different architectures to decide which one we want to focus on. And if I look at the gain bandwidth product, I can also write it in this factored form here. This one is only dependent upon the process, and this is only dependent upon the design. So similar observation for the gain bandwidth product, process dependent and architecture dependent. I'm going to look at another parameter domain. Remember, there are two degrees of freedom. So we talked about small signal parameter domain, didn't give us much insight design. We talked about the natural parameter domain. It's convenient to work with, but we have complicated expressions, and our expressions for gain and gain bandwidth product depend jointly in a nonlinear way on both of those parameters. Let me consider this as a parameter domain: the power dissipation and the excess bias. The excess bias is VGSQ minus VT. I can go back and calculate the gain now. GM over G out. GM is 2 IDQ over V excess bias. G out is 1 over lambda IDQ. IDQs cancel. And this is 2 over lambda V excess bias. And the gain bandwidth product is GM over CL. GM over CL. And the power is equal to the product of IDQ and VDD, VDD minus VSS, So I can express the gain bandwidth product in this form. Now, notice that this has a similar property to what we had in the natural parameter domain. In this case, the voltage gain is a function of 2 over lambda, which is characteristics of the process, times 1 over p excess bias, which is characteristics of design. And the gain bandwidth product is equal to some of these characteristics of the process and the constrained PDD and CL, and my parameters in the parameter domain. Let me look briefly at these two terms there. This term here is, yes?
When you're saying gain bandwidth product, so GB, are those two separate variables just multiplied?
No, it's GB.
Okay.
It's the
So
product of 3 dB bandwidth and the DC gain.
Oh,
Same GB that you talked about in 230. Good question. Any other questions? Okay, so in this alternate parameter domain with P and Vx as bias, again, 2 degrees of freedom here, right? The gain is 2 over lambda times 1 over Vx as bias. This is not a function of the design. And the GB is equal to 2 over PDD CL. This is not a function of the design, and this is not a function of the process. So that's process dependent, and that's architecture dependent. Again, we can compare different architectures because we can always write it in this form. Whatever is multiplying this term here will determine the characteristic of that architecture. Yes?
So VEB is it's V and Q minus VSS, whatever I have.
Yep, that's correct.
It's minus VT, right?
Yep.
But well, we were trying to avoid the change of if I change IDQ in the natural design parameter.
Yeah.
I was trying to avoid if I change IDQ for GB, I don't want to change AV. But now it's happening the same here. If
IDQ might be changing. IDQ might be changing. W over L might be changing.
I mean, we were trying, if I wanted to in GB, I don't want to change AV. But now it's still the same problem.
No, there's a big difference here. If I want to set the voltage gain with this architecture, it's only dependent on VXS bias. So I set VXS bias, the gain is fixed. After I set VXS bias, then I can come over here and set the power to get the GB. I definitely don't have that property if I use a natural parameter domain. I don't have that property if I use a small signal parameter domain. Make sense? So we can look at it. In fact, we can look at a design algorithm here very easily to get a certain gain bandwidth product. First set the gain up by picking VXS bias, then look at the power to get GB. This also gives some other insight into something that's really important. Power is a very valuable resource. If you want speed is associated with high gain bandwidth product, is going to cost you power. If you want 10 times the speed for the same gain, 10 times the power. No free lunch here. Make sense? Power and speed, this very clearly shows the power-speed relationship. So this alternate parameter domain gives considerable insight into design. It's easy to map, I didn't do it, but it's easy to map from this alternate parameter domain back to the natural parameter domain. We can write closed form expressions, and once we have P and Vx as bias, we can easily get W over L and IDQ. When we do the design, we need W over L and IDQ, right? But there's a closed form simple expression that maps between these two parameter domains. The alternate parameter domain provides modest parameter decoupling because in this case, the gain expression only depends on one of the parameters, not both of them. these quantities, if I divide AD0 by 2 over lambda, that becomes a figure of merit for the gain, and GB divided by this becomes a figure of merit for the gain bandwidth product. So I can use these figures of merit for comparing different amplifier structures. It may be the case that you have two different architectures that have a different relationship between gain bandwidth product and power. This structure here has this relationship. If you had another one that had a factor of 5 in front of this P here, then that would be a much more power efficient amplifier structure. Make sense? Does anybody have any questions? Yes?
Is it AV and GB the only like actual parameters or values that we want to manipulate?
No, they aren't.
Amplifier performance? Or these are just two
They
basic
aren't.
ones?
But if you look at the gain of an amplifier, these are usually the two most important.
Okay.
An op amp has a gain A0, it has a bandwidth, and the product of these is the gain bandwidth product. Those are usually the two most important parameters in those
There's
amps.
other stuff we'll go into probably.
That's right. Now when you become over-constrained, you have to start making trade-offs. But this parameter domain here, this alternate parameter domain, is still very useful if you're going to consider other parameters as well. Any other questions? It brings me to the most important slide. That's all for today, thanks.
Yeah.